Hello students, this is Dr. Faizan Mirza. We are discussing ventilation and diffusion. The content that I am covering here includes how the volumes and flows can be used to explain how much of fresh air goes into the lungs every time you breathe in and breathe out. What exactly do you mean by ventilation? How the air which is expired and the one which stays in the dead space, how it is dependent on every breath that you take. What is the concept of the anatomical dead space and how nitrogen washout you can be used to describe this. I'll also refer to how the regional changes can be seen in ventilation. This is what I'll be covering in this video. So starting off with this flow and the volumes, we have already covered this, that the tidal volume is 500 ml and 150 ml of the air stays in the anatomical dead space, and which means actually that if you subtract 500 from and 150 from 500, we get 350 ml. So 350 ml of the air actually goes in your alveoli, and this is the fresh air which is going. So exact 500 will not go there. And this air which will go there, if the breathing frequency is 15 per minute. So if you calculate the respiratory ventilation, so we can say that if 350 ml of fresh air is going and the person is taking 15 breaths per minute, so about 5250 ml per minute of fresh air actually is going. So this is what ventilation actually means, that total ventilation per minute can be calculated by simply multiplying the respiratory rate and tidal volume, which was 515, and we get 7500 ml per minute. But this is not exactly the case, because exact 500 is not going. We have to subtract 150 which stays in the anatomic dead space, and the answer, which is 350 ml, is what's going into the alveolar ventilation. When we are comparing the ventilation, we use this V to denote the volume, and the subscripts of TDA are used to denote tidal. So this is ventilation of tidal volume, the ventilation which is responsible for being in the dead space, and ventilation that goes to the alveolar region. So this formula Vt is equals to Vd plus Va actually tells you how the ventilation is dependent on dead space and alveolar both. So the volume of air that you expire, the ventilation of expire, when we use V dot, this means volume per unit time. So volume per unit time expired is equals to volume per unit time present in the dead space plus volume per unit time in the alveolar region. The alveolar ventilation then becomes volume per unit time in the alveolar air, which equals to the volume of air ventilated per minute, or you can say expired, subtracted from this volume which is in the dead space, which we actually have done just a few moments back. Anatomic dead space. The basic concept of anatomic dead space is that the volume of the conducting airways holds about 150 ml of air, which stays there in this, which stays trapped in this region. This air will stay there, and when you exhale, this 150 ml will go into the alveoli to displace the exhaled air. So 150 ml will go into the while you are rebreathing or taking the next you can say breath of air. How the anatomic dead space can be measured? It can be measured by using Fowler's method. The Fowler's method makes the person breathe to a valve box, and a sampling tube is attached at the lips of the subject, and the subject will be taking a breath of 100% pure oxygen, and then the person will start to exhale, and the nitrogen concentration in the exhaled gas will start to increase gradually until a plateau is reached. So this is what we see. We see this kind of a graph in which you can see that this is just, I'm telling about the physiologic dead space and the anatomic dead space. In normal subjects, the anatomic dead space and the physiologic dead space are equal. They stay the same. But in patients suffering with lung disease, the physiological dead space might be larger while the anatomic dead space stays the same. So anatomic dead space is basically just the region in which the conducting airways in which the air stays trapped, and it's not reaching the alveoli in that tidal volume. So this graph shows to you the nitrogen concentration. At the start of inspiration, this is the amount of nitrogen already there. The person inhales pure oxygen, so the volume of the concentration of nitrogen drops sharply. and this is displaced by the pure oxygen that the person inhaled. Then the person starts to exhale, and when the person is exhaling, the exhaled nitrogen comes out, and at the lips of this subject, the recorder will record the nitrogen content in the nitrogen meter. So we see that after a gradual rise of nitrogen which is exhaled out, the nitrogen concentration starts to plateau. This plateau represents pure alveolar gas, which means that all the gas from the alveoli is being moved out. So this is how the anatomic dead space is calculated, that this alveolar plateau, this actually tells you how much air was being held in the anatomical dead space initially. The total ventilation is the tidal volume multiplied by the respiratory frequency. Alveolar ventilation is just the amount of fresh air which is going into the alveoli, or you can say the difference of Vt and Vc multiplied by N. Anatomic dead space I've discussed is about 150 ml, and physiologic dead space is the volume of gas that does not eliminate carbon dioxide. So the carbon dioxide that stays within the lung actually represent your physiologic dead space. And already discussed that two dead space are same in normal individual, but raised in those the physiologic dead space might be raised in the individuals who have a respiratory disorder. When we compare the regional differences mean this is the upper region or upper zone of the lung, this is the middle zone of the lung, this is the lower zone of the lungs. When we discuss about ventilation means how much new gas can go. So this radiation counters are used, and in this experiment we use xenon counters. So the xenon gas is inhaled, and the amount of xenon which can go in every region of the lungs, which mean the lower zone, the middle zone, and the upper zone, is actually monitored by these radiation counters. We see that the highest ventilation is in the lower zone. So this actually tells you that the lungs seem to have a regional difference in ventilation. Highest ventilation is present in the lower zone, lesser ventilation is present in the middle zone, and the uppermost zone is having the least ventilation in the lungs. That's all from my side. Thank you so much.